Welcome to The Explainer. So today we're taking a really fascinating journey into the technology that quietly guides our modern world. We're going to break down an incredible paper by Husam Hinyanda. It's titled Advanced GNSS System Design and Analysis, and it essentially demystifies the entire end-to-end processing chain of a GNSS receiver. We're talking about moving from raw, invisible radio signals all the way to that precise 3D location on your screen. But before we get into the heavy math, let me just ask you a question. How does your phone actually know where you are? You open a map app and instantly a little blue dot appears. We literally take it for granted every single day, but it's effectively an invisible magic trick. And what's really interesting about this is that the trick doesn't start in your hand. Actually, it starts a staggering 20,200 kilometers out in space. Okay, let's dive into our roadmap for today. We'll quickly cover 1. The architecture of GNSS. 2. Constellations and geometry. 3. Catching the signal. 4. Solving the navigation equation. And finally, 5. Building a virtual receiver. All right, part 1. The architecture of GNSS. Breaking down the system. So before we get into the intricate math of how we process these signals, we really need to appreciate the sheer cosmic scale of this global navigation network. It's broken down into 3 distinct segments. First up, you have the space segment, which consists of the constellations of satellites up in orbit. Then there's the control segment, and those are the massive ground tracking stations that make sure everything runs smoothly. And finally, the user segment, which is the receiver right there in your device. Now, our explainer today is going to zero right in on the intricate math powering that user segment. Moving on to part 2, constellations and geometry, the space segment. I want you to literally look up and imagine where our signal actually originates. That origin point, it's roughly 20,200 kilometers above us. GPS satellites operate in what's known as medium Earth orbit. They're continuously beaming radio signals through the freezing vacuum of space, down through our atmosphere, and straight into the antenna inside your smartphone. It's wild to think about. But here's the thing. One signal simply isn't enough. So the absolute critical point is this number right here, 4. For accurate positioning, your receiver strictly needs at least 4 satellites in its view. Why 4? Well, because the software has to mathematically solve for 4 distinct variables: your latitude, your longitude, your altitude, and crucially, the receiver's internal clock bias. That clock bias is essential to keep everything perfectly synchronized with the satellites. All right, let's hit part 3, catching the signal, PRN, and correlation. Here, we hit a massive engineering hurdle. Every single satellite broadcasts on the exact same frequency. So how in the world does your phone avoid just a jumbled mess of static? The elegant answer lies in PRN, or pseudo-random noise. Think of this like being at a super crowded cocktail party. Everyone's talking at the exact same time in the exact same room. But if someone across the room calls your specific name, you can somehow tune out the background noise and hear them, right? Well, each satellite transmits a unique gold code, which acts like its own specific voice. This allows multiple signals to share one frequency through code division multiple access, or CDMA. Because these codes have incredibly high autocorrelation and very low cross-correlation, your phone can mathematically isolate one specific voice from the crowd perfectly. To actually isolate that voice, the receiver has to do some heavy mathematical lifting. What's so fascinating about this cross-correlation equation is that your device is taking the incoming signal, S of n, and multiplying it by a local replica that it generates internally, P of n minus tau. It essentially slides its own internally generated code over the incoming noise from space. It shifts the timing bit by bit, just constantly looking for a perfect mathematical match. And when it finds that match, boom, the equation yields this massive sharp peak. Finding this correlation peak is the magic moment. It unlocks the exact time of arrival of the signal. Because we know how incredibly fast radio signals travel, the speed of light, we can use that exact time to calculate our initial distance estimate from the satellite. In GNSS terminology, this critical initial distance measurement is called our pseudo-range. Which brings us to part 4, solving the navigation equation, iterative least squares. Okay, so we have our pseudo-ranges from the satellites. But now, we have to survive a gauntlet of mathematical decoding to turn those raw distances into your actual location. This highly nonlinear equation right here represents the complex relationship between the measured pseudo-range, represented by rho, and the user's actual 3D coordinates, which are the lowercase x, y, and z. Because of all the square roots and the squared terms, you can't just solve this algebraically in one easy step. It's a seriously complex geometry problem. So how do we actually solve it? We use something called iterative least squares. We can translate this from dense Taylor series math into a brilliant plain English system of just, well, smart guessing and refining. Step 1. The receiver makes a wild but educated initial guess of where it might be. Step 2. It linearizes that terrifying equation we just looked at using a Taylor series expansion around that initial guess. And step 3. It calculates an update vector, delta x, using what's called an H-geometry matrix. Basically, it guesses, checks the math, figures out the error, mathematically updates the guess, and repeats that whole process until it absolutely nails it. All right, part 5, building a virtual receiver, MATLAB implementation, and results. The absolute best way to prove this complex math actually works isn't just to write it down on a whiteboard, it's to simulate it. And that is exactly what the author of this paper did by building a virtual receiver using MATLAB. Now, the simulation didn't just use fake arbitrary numbers to make things easy. No way. To make this a true test, the MATLAB code utilized real-world ephemeris data, meaning the actual orbital paths of real satellites. It parsed this data via an authentic RINEX file format. This guarantees that the satellite coordinates fed into the iterative least squares engine were completely authentic. It mirrors exactly what a physical hardware receiver experiences when it's out in the field. And the results are genuinely fantastic. The algorithm only needed 4 to 6 iterations to zero in on the final location. That entire process of guessing and refining we talked about, it happened in an absolute flash. The positioning error margin was less than 5 meters. The math works perfectly, pinpointing a highly accurate 3D position from signals that originated tens of thousands of kilometers away. Let's jump into the discussion and critical analysis. The geometry trap. Okay, here is the catch. Even if your receiver's math is absolutely flawless, the system has a critical physical vulnerability that the paper analyzed in depth. That vulnerability is known as the dilution of precision, or DOP. DOP is a critical factor that measures how the physical geometric arrangement of the satellites up in the sky affects the mathematical accuracy down on your device. It is essentially the ultimate geometry trap. If the satellites happen to be bunched up in the wrong part of the sky, well, your phone's math will fail, and your map will be entirely wrong. Let's see how this plays out by comparing 2 scenarios. Item 1, clustered satellites. If the 4 satellites your receiver locks onto are all clustered together in one tiny corner of the sky, it drastically increases your horizontal DOP. This leads to severe positional calculation errors. Basically, your blue dot will jump all over the place. Conversely, item 2, distributed satellites. If they are spread wide across the horizon, you get a really healthy distribution. This yields a low DOP and ensures the high accuracy that the simulation successfully utilized. This brings us perfectly to the paper's conclusion. Hanande writes, "This project successfully demonstrates the complexity of GNSS receivers. By processing real orbital data and performing high-speed correlation, we replicated the operation of a modern GPS receiver." I mean, it's a massive achievement to literally replicate the invisible brain inside every single smartphone using raw code. So I want to leave you with this final provocative thought. The next time you look at a blue dot on a screen, will you think of the invisible mathematical symphony happening 20,200 kilometers above you? Just think about it. A network of orbital clocks, intricate cross-correlation algorithms, and iterative least squares running constantly, just to tell you exactly where you're standing. It's just a phenomenal, invisible web of physics, math, and code surrounding us every single day. Thanks so much for joining me for this explainer, and keep exploring the amazing hidden systems in our world.